We have seen in another video how to assess standard uncertainty through the statistical analysis of a series of observations, that is, by using a type A method. This method has a serious drawback. It requires a series of measurements and therefore a statistically significant number of measurements, which is not always possible for technical reasons, for example in the case of destructive testing, or for economic or time constraints. Even in cases where it is not possible to carry out a series of measurements, it is still necessary to assess the uncertainty to be attributed to the measurement result. It is therefore necessary to use a method for evaluating uncertainty by means other than the statistical analysis of a series of observations. This is a method that the GAM refers to as a type B method for evaluating uncertainty. And what are those means? Once again, the GAM helps us establishing that the standard uncertainty can be evaluated by means of a scientific judgment based on all of the available information on the possible variability of the measurand. Let's then begin by asking ourselves what kind of information is available. Once again, the GAM provides us with useful suggestions, as it tells us that this information can be found in previous measurement data, in the experience with or general knowledge of the behavior and properties of relevant materials and instruments, in the manufacturer's specifications, in the data provided in calibration certificates, or, absent more specific information, in the uncertainties assigned to reference data taken from handbooks. Starting from this information, the operators, relying on their own scientific judgment, must identify a probability density function capable of describing the distribution of values that could be attributed to the measurand and assess its standard deviation and thus the standard uncertainty to be assigned to the measurement result. The GAM specifies that the proper use of the pool of available information for a type B evaluation of standard uncertainty calls for insight based on experience and general knowledge and is a skill that can be learned with practice. This clarification is important because it helps us understand that the evaluation of measurement uncertainty is not a routine activity, but one that must be considered and adapted to each specific case based on experience gained through practice. In general, the information most commonly used in the type B method comes either from calibration certificates or from the manufacturer's technical specifications. We will see how to use the former when we will discuss calibrations. Now let's look at an example of how to use the manufacturer's specifications. Let's consider the same digital voltmeter as the one we used when we considered an example of uncertainty evaluation using a type A method. Let's suppose we have measured just one value of DC voltage, for example the value of 8.00738 volts, which is one of the values we measured in the aforementioned example. To measure this voltage, we used the 20-volt range. The manufacturer's technical specifications for DC voltage measurements are those shown in this table, where the row corresponding to the 20-volt range is highlighted. In the fourth column, the accuracy specifications are given, expressed as a percentage of the value read, in this case 0.015%, to which a percentage of the full scale must be added, in this case 0.004% of 20 volts. From this data, an interval about the measured value is obtained, whose half-width A is given by the equation shown here. According to the manufacturer's specifications, all possible values that can be attributed to the measurand fall within this interval. It is now necessary to determine the probability density function that best describes the distribution of values that could be attributed to the measurement. In this case, we know that these values are distributed over an interval of finite width 2a, and we have no further information about how they are distributed. We can therefore make reference to the principle of maximum entropy, which in this case leads to considering a uniform probability density function. Probability theory tells us that the standard deviation of this distribution is given by its half-width divided by the square root of 3, as you can see here. The standard uncertainty given by this standard deviation with the values found for the half-width A of the interval is therefore 1.2 millivolts. We have therefore seen with this example which steps to follow in order to assess the standard uncertainty using a type B evaluation method. We have already seen how to assess the standard uncertainty for the same instrument and under the same measurement conditions using a type A evaluation method. We would expect to find similar values, whereas the standard uncertainty assessed using the type A method is almost 2 orders of magnitude smaller than the one just evaluated with the type B method. Why is that? The answer lies in the different set of information we have considered. When we used the type A method, we repeated the measurements under the same conditions in a short period of time and without any variation in the influence quantities such as temperature, humidity, supply voltage, and so on. When we used the type B method, we relied on the manufacturer's specifications, which take into account the variability of the result provided across the entire batch of instruments produced and within the full range of permitted variability for the influence quantities. It is therefore normal to find a greater value for uncertainty. When we used the type A method on this same instrument, it was as if we had randomly selected one instrument from all of those produced and fixed a value for the influence quantities within the specified range. The variations in the results obtained in this case are typically generated by short-term noise. To summarize, we have completed the analysis of the methods recommended by the GAM for evaluating the standard uncertainty. We have analyzed the type B method that is based on methods other than the statistical analysis of series of observations. We have also seen what information can be used to assess the standard uncertainty to be associated with the measured value and thus obtain a measurement result. We have also considered an example of the application of this method.